Imagine holding a dinosaur tooth, a relic from over 66 million years ago. It's not just a fragment of a long-lost creature, but a direct link to a world that existed before humans ever walked the earth. The weight of it in your hand is the weight of deep time itself, a tangible connection to an age of giants and ancient forests. This isn't just a piece of ancient bone, it's a time capsule, preserving secrets about the world it came from. Every groove and ridge on its surface tells a story, and every mineral that replaced its original tissue holds a clue to the environment it once knew. Each layer of enamel is like a page in a diary, recording the chemistry of the air, water, and climate of the Mesozoic era. These microscopic layers grew year by year, capturing subtle shifts in the world, droughts, floods, even volcanic eruptions, etched into the very structure of the tooth. These teeth are more than fossils, they're geological storytellers capturing snapshots of a vanished world. They are silent witnesses to the rise and fall of ancient ecosystems and the dramatic changes that shape the planet. By decoding the chemical language in these teeth, we can reconstruct ancient environments and climates. Scientists can determine what dinosaurs ate, what kind of water they drank, and even how the seasons changed during their lifetimes. We're no longer limited to studying dinosaur bones for their shape or size. Now, we can peer inside, using chemistry and physics to unlock their hidden data. Advanced imaging and analytical techniques reveal secrets invisible to the naked eye, opening up new chapters in the story of life on Earth. This approach transforms fossils into scientific instruments, natural sensors that recorded their world for millions of years. Each tooth becomes a data archive, storing information about ancient temperatures, rainfall, and even atmospheric composition. Studying these ancient changes helps us understand the forces that have shaped our planet. The shifting continents, the rise and fall of sea levels, and the cycles of climate, all are written in the chemistry of these ancient teeth. The story of a dinosaur's tooth is about more than the past. It's about planetary systems, and the interconnectedness of life and environment. It reminds us that every living thing is part of a much larger story, woven together across eons. These teeth remind us that Earth has undergone dramatic transformations, with climates and atmospheres that would seem alien to us. The world of the dinosaurs was both familiar and strange, shaped by forces that continue to influence our planet today. By reading these chemical fingerprints, we gain insight into the balance of chemistry and life across time. We can trace the rise of oxygen, the shifts in carbon dioxide, and the impact of mass extinctions on the living world. The lessons locked in these fossils have powerful implications for our own future. They offer warnings and wisdom about how life responds to change, and how our actions today might echo for millions of years to come. They connect us to Earth's deep past in a profound way. Holding a dinosaur tooth is like shaking hands with history, feeling the pulse of a world long gone but never truly lost. And they challenge us to consider our place in the ongoing story of our planet, a story still being written, with us as its latest chapter. How do we unlock the secrets of a dinosaur tooth? What stories are hidden within its ancient structure, waiting to be revealed by modern science? The journey begins in the lab, where scientists focus on the tooth's enamel, the hardest, most durable part of a dinosaur's anatomy, and the best place to search for chemical clues from the distant past. Enamel is made of a mineral called bioapatite. This substance is incredibly resilient, tough enough to preserve chemical information for millions of years, even as the rest of the tooth or bone may erode away. Scientists carefully select the best preserved teeth, then extract a tiny, precise sample of enamel, sometimes just a few milligrams, using specialized tools to avoid contamination. This powdered enamel is then analyzed in a mass spectrometer, a sophisticated machine that sorts atoms by their mass and counts their types with incredible precision, revealing the atomic makeup of the sample. The key elements under investigation are oxygen isotopes, specifically oxygen-16 and oxygen-18, which are present in varying amounts depending on environmental conditions. These isotopes act as subtle markers, recording the chemistry of the water the dinosaur drank and the air it breathed, providing a chemical diary of its life. The ratio of heavy to light oxygen in the enamel reflects the environment's conditions at the time, such as temperature, rainfall, and even the sources of water available to the dinosaur. This chemical signature is a direct link to the climate and hydrology of the dinosaur's world, offering a rare glimpse into prehistoric weather patterns and ecosystems. By measuring these ratios, we can reconstruct ancient climates, using the dinosaur as a prehistoric weather station, and comparing ancient data to what we know about today's climate. The enamel's chemistry becomes a data log, capturing snapshots of temperature, rainfall, and even atmospheric composition, all locked within a single fossilized tooth. This method allows us to ask questions about the world that would otherwise be impossible to answer. Questions about ancient seasons, droughts, and migrations. Each tooth becomes a record of the environment preserved in stone, and a silent witness to the world in which dinosaurs lived and thrived. Through this process, we turn fossils into windows on the deep past, transforming ancient remains into scientific evidence. And with every analysis, every new discovery, we come closer to understanding the world as dinosaurs knew it, one tooth, one story at a time. The oxygen isotope ratio in a dinosaur's tooth acts as an ancient thermometer. The process of forming enamel is temperature dependent, so the ratio reflects both the dinosaur's body temperature and the climate it lived in. By measuring these ratios, scientists can estimate whether dinosaurs were cold-blooded or warm-blooded, and the evidence suggests they were somewhere in between. The isotopes also reveal the temperature of the water dinosaurs drank, which is tied to local air temperature. By combining these signals, we can estimate the average air temperature where the dinosaur lived. A single tooth can give us a temperature reading from the Jurassic or Cretaceous. We're not just guessing about ancient climates, we're measuring them, using the teeth of long-extinct giants. When scientists analyzed dinosaur teeth from the Jurassic and Cretaceous, they uncovered remarkable evidence of a much warmer world than we know today. These ancient teeth, preserved for millions of years, hold chemical clues about the air and climate in which dinosaurs once thrived. The secret was in the air. High levels of carbon dioxide, or CO2, trapped heat and created a true greenhouse planet. This greenhouse effect was far more intense than anything we experience in the modern era. CO2 levels during the Mesozoic often exceeded 1,000 parts per million, far higher than today's levels, which hover just above 400. These elevated concentrations of greenhouse gases dramatically altered the planet's climate. This supercharged greenhouse effect meant little to no permanent ice at the poles and lush forests in places now frozen. Even the polar regions, which today are icy and barren, were once covered in dense green vegetation. The temperature difference between equator and poles was smaller, creating a stable, warm, and humid climate that spanned much of the globe. This allowed life to flourish in regions that are inhospitable today. These findings, drawn from fossil chemistry, provide a direct record of Earth's climate sensitivity to CO2. By studying these ancient signals, scientists can reconstruct the environmental conditions of the distant past. They show us how the planet responds to high greenhouse gas levels, not as a theory, but as a measurement from the real world, preserved in stone and bone. The story is clear. More CO2 means a hotter planet with profound changes to ecosystems and landscapes everywhere. This ancient truth is a vital baseline for understanding today's climate changes, reminding us that the atmosphere's composition has always shaped the fate of life on Earth. High CO2 didn't just warm the planet, it fueled a global explosion of plant life. This CO2 fertilization let plants grow faster and larger, covering the world in dense vegetation. For giant herbivores like Brachiosaurus, this meant endless food, enough to support their massive size. The abundance of plant eaters, in turn, supported huge carnivores like Tyrannosaurus rex. The energy flowed from sun to plant to herbivore to predator, all powered by the chemistry of the atmosphere. The shape and wear of dinosaur teeth reveal their role in this food web. Herbivores adapted for stripping foliage, carnivores for tearing flesh. Each tooth is a link in a chain connecting air, plants, and animals. The size and scale of dinosaurs were direct consequences of their environment's chemistry. This deep connection between atmosphere and life is a powerful lesson in planetary systems. Life shapes and is shaped by the world it inhabits. Where did all that CO2 come from? The answer: massive volcanic eruptions. Events like the Deccan Traps in India released vast amounts of lava and greenhouse gases, fundamentally altering the climate. These eruptions left chemical signatures in dinosaur teeth, showing rapid environmental changes. Initially, volcanic dust cooled the planet, but the long-term effect was intense warming from lingering CO2. Teeth from this era capture these wild climate swings, revealing how life responded to sudden planetary upheaval. The Deccan traps began before the asteroid impact that ended the dinosaurs, stressing ecosystems to the brink. The climate was already unstable, making survival difficult for many species. The story in the teeth suggests the world was in turmoil before the final extinction blow. Volcanism and climate are deeply intertwined, shaping the fate of life on Earth. Studying dinosaur teeth isn't just about the past, it's a warning for our future. These fossils provide real-world evidence of how Earth behaves under high CO2 conditions. The data helps refine climate models, testing their predictions against ancient reality. By inputting Cretaceous CO2 levels, scientists can see if models accurately recreate the warm, ice-free world of the dinosaurs. This research also sheds light on mass extinctions, revealing how ecosystems collapsed during times of rapid change. Understanding these patterns is crucial for protecting today's biodiversity. The story of the dinosaur tooth is a cautionary tale. Earth's climate can change dramatically and quickly. The hothouse world of the dinosaurs was marked by instability and extinction during transitions. As we raise CO2 levels today, the echoes from the Mesozoic warn us of profound, lasting consequences. The past is speaking to us, if we're willing to listen. Analyzing tooth enamel is revolutionizing paleontology. We're no longer limited to bones, now we can read the chemical diaries inside each tooth. By sampling different layers, scientists can track seasonal changes, migrations, and even droughts in a dinosaur's life. Teeth from around the world let us map ancient climates in detail, moving from blurry averages to high-resolution reconstructions. This method works for any well-preserved fossil, from dinosaurs to mammals to marine reptiles. The chemical story in enamel is a vast library, and we're just learning to read it. Each tooth is a personal diary and a piece of a global puzzle. The more we analyze, the clearer our picture of Earth's history becomes. The future of this research is bright. As technology advances, we'll extract more data from even tinier samples, using new isotopes to track migration, diet, and climate. The goal? A continuous high-resolution record of Earth's climate built from fossils of all kinds. Each fossil is a pixel in the grand image of our planet's history. This global effort will help us understand natural climate rhythms and tipping points. The past is a user's manual for Earth, and every tooth adds a new chapter. We are part of a long, continuous story of life and change. The bones and teeth of ancient life are speaking to us. We just have to listen.